In this talk, we will work with real weighted directed graphs. We will denote by n the number of vertices and by m the number of edges. Our focus is on the minimum weight cycle problem, one of the most fundamental graph problems. Given a directed graph G, we want to find the minimum weight phi of G of a cycle in the graph or decide there is none. Let delta st denote the distance from S to t in G. There is a very simple algorithm for computing the minimum weight cycle. Namely, it is enough to take the minimum over all edges uv of the weight of that edge plus the distance from v to u. This corresponds to guessing some edge on the sought cycle and extending it to a shortest possible cycle using a shortest path between the head and the tail of that edge. So it follows that the minimum weight cycle problem is trivially reducible to the all pairs shortest paths problem, since by solving APSP we obtain all the needed distances to evaluate this formula. The best known algorithm for minimum weight cycle runs in order nm time, which is only a logarithmic factor faster than running APSP. Actually, there exist better algorithms for some special cases like dense unweighted graphs, but our main focus in this talk is on sparse, real weighted directed graphs. A widely believed APSP conjecture says that computing all pairs shortest paths requires cubic time in the number of vertices. Wasilewska, Williams, and Williams proved that this conjecture implies that the minimum weight cycle problem also requires cubic time. So APSP conjecture implies that the classical approaches like Floyd-Warshall are near optimal for both APSP and minimum weight cycle for dense graphs. There are some other good reasons to believe that the state-of-the-art algorithms for sparse graphs are also the best we can hope for. But the bottom line is that in the static setting, APSP and minimum weight cycle are equally hard. Now consider the fully dynamic setting where the graph is subject to edge insertions and deletions. Demetrescu and Italiano showed that one can maintain APSP in near quadratic amortized time per update. This is near optimal if we want the distance matrix to be maintained explicitly, since even a single edge update can change all the n-squared pairwise distances of a sparse graph. That algorithm is even slightly more general, and the update bound holds even if all edges incident to a single vertex are changed. However, it is not known whether one can reduce the amortized update time significantly at the cost of using some non-trivial query procedure. A good question to ask is whether some problems that are trivially reducible to APSP are easier in any way in the fully dynamic setting. This is especially interesting for problems whose output is a single number, like diameter, radius, or minimum weight cycle. Note that for these problems, the n-squared output lower bound does not apply. And indeed, this question has been asked before. Ancona et al. Proved that under the strong exponential time hypothesis, the best you can do for dynamic diameter is to maintain APSP dynamically and explicitly. This is still true even if the graph remains sparse at all times and we allow approximation factor less than 3/2. They also showed a similar conditional lower bound for radius. But does a similar conditional lower bound hold for minimum weight cycle? The fundamental difference between minimum weight cycle and diameter or radius is that computing the former requires only m entries of the distance matrix, whereas for the latter, it seems we have to inspect all the n-squared entries in order to compute the answer. In our paper, we show that indeed the situation is different for minimum weight cycle. Namely, our first result is a fully dynamic algorithm maintaining a 1 plus epsilon approximate estimate of the minimum weight of a cycle in roughly order m log w over epsilon amortized amortized time per update. Here we assume that the weights are real numbers between 1 and w. Note that for a small constant epsilon and sparse graphs, the amortized update time is near linear in n, which is in sharp contrast with the quadratic conditional lower bounds for diameter and radius. Moreover, for vertex updates, this bound is near optimal simply because n updates are enough to compute the minimum weight cycle of a static graph approximately, and it is known that under so-called k-cycle hypothesis, finding the minimum weight cycle with multiplicative error less than 2 requires order mn time. Our second result is an exact algorithm maintaining the minimum weight cycle in roughly order mn to 2/3 worst case time per update. This algorithm is Monte Carlo randomized. So again, for sparse graphs, this bound is subquadratic. If we are only interested in the minimum weight of a cycle, the exact algorithm works against an adaptive adversary, since the answer is always unique. However, if we are also required to produce some actual cycle of minimum weight, then we need to assume an oblivious adversary to have correctness with high probability. Let us now briefly mention some implications of the approximate algorithm in dynamic algorithms on planar graphs. If we consider only single edge updates, then our algorithm can be viewed as a reduction to a fully dynamic exact distance oracle. More specifically, recomputing the minimum weight cycle after a change can be handled using constant amortized number of edge updates and queries issued to a dynamic distance oracle. While dynamic distance oracles with sublinear update and query bounds are not known for general graphs, they do exist for planar graphs, and therefore we immediately obtain a fully dynamic approximate minimum weight cycle algorithm for planar graphs with roughly order n to 2/3 amortized update time. But this is not all. Even more importantly, via well-known duality-based reductions, we also obtain similar amortized update bounds for approximate max ST flow and global mean cut for dynamic plane embedded directed graphs. In fact, it seems that no sublinear bounds have been previously described for these problems on directed plane graphs. However, exact dynamic algorithms for these problems were known before, but for undirected plane graphs. Let us now describe the approximate algorithm, as it is very simple. Recall that G has real weights between 1 and W. As a result, if G has a cycle, its length has to fall between 1 and n times W. We solved the approximate problem using a few instances of what we call the threshold cycle detection problem, defined as follows. Given a non-negative threshold parameter mu, we would like to maintain, subject to fully dynamic vertex updates, whether the minimum weight of a cycle in G is less than mu. How is it useful? Well, given such a dynamic algorithm, we can set it up for thresholds equal to integer powers of 1 plus epsilon that lie between 1 and nw. There are order log nw over epsilon of those. And we can maintain the minimum used mu, for which the threshold cycle detection data structure says yes. It is then easy to see that indeed that threshold approximates the minimum weight of a cycle within a factor of 1 plus epsilon. So the update time is order log nw over epsilon times the update time of the threshold cycle detection data structure. Let us now discuss the threshold data structure. So the first very simple but useful observation is that we can compute the minimum weight of a cycle going through some chosen vertex v in order n plus n log n time, which is the running time of Dijkstra's algorithm. This is simply because in the formula for computing the minimum weight cycle, after we fix the incoming edge of v, we only need the distances from v in G. and those can be found using a single source shortest paths computation. Now, the algorithm keeps the edge set of the graph partitioned into two sets, E0 and E1. These sets should always maintain the following invariants. First of all, the subgraph G0 induced on the subset E0 should not contain a cycle of weight below the threshold. Moreover, if E1 is non-empty, then the whole graph G actually contains a cycle whose weight is below the threshold. Since E0 and E1 form a partition of E, these invariants imply that G has a cycle below the threshold if and only if E1 is non-empty. Now, the update procedures are as follows. Suppose the invariants are satisfied before the update. Consider an insertion of edges centered at V. If E1 is empty, we check whether adding the new edges around V to G0, which then equals G, would introduce a new cycle below threshold in G0. Such a cycle has to go through V obviously, so this costs a single SSSP run. If no such cycle arises, we move the new edges to E0 and otherwise they are put in E1. It's easy to check that the invariants are satisfied afterwards. Now consider the deletion. Actually, a single deletion can remove any subset F of current edges, not just those around some single vertex. The first step is to remove F from both E0 and E1. The removal might only break the second invariant, so we attempt to move edges from E1 to E0 in order to fix it. We do so starting from least recently updated vertices, and again, we run one single source shortest paths computation per move attempt. Here's an example run of the algorithm. We start with an empty graph. Now, an insertion centered at V1 comes. Since E1 is empty, we test whether we can insert the new edges to G0. Well, of course we can, since G0 is empty and there are no cycles there. So V1 gets moved to G0. Now another insertion comes, this time centered at V2. Again, E1 is empty, so we can check what would happen if V2 went to G0. Well, suppose a cycle below threshold would arise there, so V2 gets moved to E1. Now we have one more insertion around V3, which immediately gets moved to E1 since E1 is non-empty. And the same happens with the next insertion around V4. Now suppose the edges around V3 are deleted. Since G0 contains no edges incident to V3, this cannot change the minimum weight of a cycle in G0 plus V2, so the attempt to move V2 will obviously fail. But now, let the next deletion remove just a single edge incident to V1. Since G0 shrinks, this may cause G0 plus V2 lose its minimum weight cycle. And suppose this is indeed the case. Then we move V2 to G0, but we are not done yet. We need to try to move V4 to E1 as well. If G0 plus V4 still doesn't contain a cycle below the threshold, we move V4 to G0 as well. And we are finished now with processing this deletion, since E1 is now empty. Let us now analyze the threshold cycle detection algorithm. Clearly, the insertion always amounts to at most one SSSP run, so its worst case cost is order n plus n log n. But when handling a deletion, there might be multiple SSSP runs. We charge the cost of the SSSP run preceding the move of a vertex U to G0 to the insertion around V corresponding to that move. However, the cost of at most one SSSP run preceding the loop termination, when we fail to move some vertex to G0, is charged to the current deletion. As a result, at most 2 SSSP runs are charged to each update operation. And we conclude that the amortized update time is order n plus n log n. The threshold cycle detection data structure can also be extended to handle negative edge weights within the same time bound. For the special case of zero threshold, which can be viewed as fully dynamic negative cycle detection, we show a different algorithm with order n plus n log n worst case time. This algorithm proceeds, roughly speaking, via a reduction to dynamic minimum cost matching. We actually need that one in our exact dynamic minimum weight cycle algorithm. So once again, with this dynamic threshold cycle detection algorithm, we get an approximate dynamic minimum weight cycle algorithm slower only by a polylog factor. Now let us move to a short overview of the exact algorithm. To obtain the exact result, we consider a generalization of the fully dynamic APSP algorithm that we call fully dynamic multiple pairs shortest paths. In this problem, we are given k fixed source target pairs, and we only want to maintain the distances between these pairs under vertex updates. Recall that in order to compute the minimum weight cycle, we only need to look at m entries of the distance matrix. The obvious idea to solve this problem is to generalize one of the known fully dynamic APSP algorithms. Unfortunately, many of those, like the algorithm of Demetrescu and Italiano, seem to have an inherently quadratic update procedure that computes paths in an inductive way and thus may require to operate on all the n squared source target pairs and not just the k pairs of our interest. Luckily, one of the known fully dynamic APSP algorithms, that of Abraham et al., uses a different approach. We managed to generalize that algorithm in a non-trivial way and show that multiple pairs shortest paths can be maintained in roughly order n plus k times n to 2/3 worst case time per update. This is then used for dynamic minimum weight cycle with k set to m. Unfortunately, the changes we make to the algorithm of Abraham et al. Are pretty low level and require a good understanding of that previous work, so we will not able to cover them in detail in this talk. For those of you that are familiar with that work, the key differences are as follows. First, we use a weighted congestion scheme when precomputing alternative low-hop paths so that we can take advantage of the sparsity of both the graph and the set of source target pairs of our interest. And we use even smaller sketch graphs in order to rebuild low-hop paths destroyed by deletions. To conclude, in our paper we showed fully dynamic algorithms maintaining the minimum weight cycle of a real weighted directed graph. For sparse graphs, our approximate algorithm has near linear amortized update time, which is close to optimal, whereas the exact algorithm has truly subquadratic order n to 5/3 worst case update time. Perhaps the most natural question that arises here is whether the bound that we got in the approximate setting can be also achieved with an exact algorithm.